Welcome to The Explainer. Today, we're diving into a massive planetary mystery happening right beneath our feet. We're going to explore some groundbreaking research by Kevin L. Brown, who is a dedicated researcher, inventor, and author. He's proposed a totally fascinating new way to understand the beating heart of our planet, called the triune harmonic dynamics hypothesis. So let's jump right in and uncover the hidden forces shaping the Earth. For decades, scientists have known that our planet's magnetic north and south poles occasionally just swap places. Imagine looking at your compass, and instead of pointing to the Arctic, it suddenly points straight to Antarctica. Crazy, right? But the exact trigger for these flips has actually remained a huge puzzle. The existing understanding leaves us with a pretty major problem. It kind of treats these flips like random glitches in the Earth system without any clear, predictable cause.
And guys, this isn't just a one-time fluke. According to NASA's paleomagnetic records, which is basically just the study of ancient magnetic fields trapped in rocks, this massive global flip has happened 183 times in just the last 83 million years. That is a whole lot of flipping. It tells us this is clearly a repeating process, leaving us to really wonder, what exactly is pushing the system to flip so many times?
Here is our roadmap for the explainer today. We'll start with a magnetic field mystery, then explain the THD hypothesis, look at building structural pressure, explore testing and falsification, and wrap up with the real-world implications.
Section 1, the magnetic field mystery. Let's get right to the core of the problem. You see, the mystery isn't just that the field flips. Sometimes the field stays perfectly stable for super long periods, and other times it pulls a full reversal. But then there's this third behavior called an excursion. An excursion is basically a failed flip. The field starts to weaken and wander around, but then it snaps right back to normal without ever finishing the reversal. The big scientific problem here is explaining why the timing is so all over the place and why some flips just fail halfway through. Section 2, the THD hypothesis explained. This is where things get really interesting.
Enter researcher, inventor, and author Kevin L. Brown. He developed the triune harmonic dynamics, or THD hypothesis. This model is a total game changer because it beautifully reframes these magnetic flips. The THD hypothesis states that magnetic reversals are actually predictable structural reorganizations driven by accumulated pressure. They aren't random flukes at all. Think of it less like rolling a pair of dice and way more like bending a wooden stick until it finally snaps and resets into a new position. So, the crucial takeaway here is that our magnetic field cycles through three very distinct phases. First up is the base phase. That's where everything is nice and stable, and our compasses work just like they do today. Then comes the pressure phase, where the field gets weak, chaotic, and highly vulnerable. And finally, the integration phase hits. That's where the system releases all that pressure and settles into a brand new magnetic state, which could be a full reversal or just a return back to normal. Section 3, building structural pressure. Let's dig into how this actually happens. You can really think of Earth's core as this giant planetary pressure cooker, where stress just builds and builds until it absolutely has to be released. But instead of trapped steam, we're talking about structural pressure. This is caused by shifting, swirling liquid iron deep underground, combined with uneven heat flowing between the Earth's core and its mantle. When that heat and movement get out of whack, the pressure on the entire magnetic system starts to skyrocket. And that kicks off a super clear chain reaction. Step 1, the main north-south field that we rely on starts dropping in strength. Step 2, as that big field weakens, smaller, chaotic local magnetic fields start popping up all over the place. Step 3, this causes the liquid metal flow in the core to become highly unstable. And finally, step 4, the pressure crosses a critical threshold. It literally forces the whole system to snap into a full magnetic reorganization just to release the stress. Section 4, testing and falsification. Now, how do we know this actually holds water? Well, a scientific hypothesis is only as good as our ability to test it. That brings us to our validation test mechanisms. We can check Kevin L. Brown's model by looking closely at geological history. If THD is right, the probability of a magnetic flip should go way up whenever the main magnetic field stays weak for a long time. We should also see those temporary excursions grouping together during known high-pressure periods in Earth's past. Plus, the rocks themselves should show a clear drop in magnetic strength right before any major transition happens. But on the flip side, we have strict falsification parameters. This is what makes it strong science. The THD hypothesis is considered valid if measuring this pressure allows us to predict reorganizations better than just random chance. However, THD would be proven completely false if a full pole reversal happens while the Earth's main magnetic field is strong, healthy, and perfectly stable. If a flip happens without the pressure building up first, the whole theory is busted. To quote the researcher, inventor, and author Kevin L. Brown directly, he says, "If sustained high structural pressure does not produce transition, the hypothesis is false." See? That leaves absolutely no room for doubt. It ensures this framework remains a grounded, data-driven scientific tool, rather than just a guess. If the pressure is there, the system must eventually snap. Section 5. Real-world implications. Let's bring this all back home. So why does all of this deep Earth physics actually matter to us up here on the surface? Well, the truth is, we obviously can't prevent magnetic reversals. They're planetary scale events way beyond our control. But we can monitor the long-range risk to protect our modern infrastructure. Now, history shows these events are completely natural and not catastrophic extinction events that wipe out life. But there is a catch. A weakening magnetic field during that pressure phase lets in a whole lot more solar radiation from space. And extra solar radiation is terrible news for our technology. By understanding exactly where we are in the THD pressure cycle, engineers can actually proactively plan out satellite exposure. They can figure out how vulnerable our electrical power grids are to solar storms. They can even make sure our global GPS and navigation systems have backups and manage risks for aviation communications. It's extremely practical stuff. This whole model by Kevin L. Brown completely shifts our perspective. It moves us away from fearing a random planetary glitch and pushes us toward practically preparing for a predictable structural shift. And honestly, it leaves us with a massive question to ponder. If Earth's magnetic pressure is building right now, is our technology really ready for the next reorganization? It's definitely something to think about. That's all for today's Explainer. Thank you so much for joining me as we explored the fascinating depths of our dynamic planet.